All right, in this video, we're going to look at exponential functions, and we're going to do transformations on exponential functions. So we know that a basic exponential function has a base that's a constant, an exponent that's a variable, right? We can multiply this guy. We can add or subtract things to the x. We can add or subtract things to the y. Each of these values, we're going to look at how they take this basic shape and essentially move it or transform it to a new location or bend its shape. Right? So if you're familiar with transformations of other functions, they work the same way. So for starters, a is what we'll call an initial point. Right? Even if I had a basic exponential, right? If I had a multiple here, then it's going to help establish like a starting value of the values that we're looking at. Okay? If a is bigger than 1, we're going to call that a vertical stretch, right? Because a is multiplied to a y value, so it's either going to get bigger if a is bigger than 1, or it's going to get smaller if a is less than 1. So we'll call that a vertical stretch or compression. If a is negative, then it's going to reflect it over the x-axis, because all these values, right, if you apply a negative to them, they'll all become a negative y. So if these are positive y's, then we'll now have a negative y. Right? If you're familiar with geometric sequences, then we know that b is a common ratio. So if you want to think of it as that, we can still do that. So b is a value that keeps getting multiplied, right? Because the exponent is how many times we would have this guy multiplied by itself. So if the common ratio is bigger than 1, then we're going to keep multiplying by a value to get bigger. So as x gets larger, right, the function is going to increase, or visually it's going to go up to the right. If the base is between 0 and 1, then that means that we're essentially dividing by values. So as x's get larger, we're going to divide them away to decrease, or visually the function is going to go, the graph is going to go down to the right. Now, the h and the k value are still going to represent a horizontal shift, right? Because if I add or subtract values to x, that's going to affect the graph in the x direction. If I add or subtract values to the y, then that's going to move it up or down, right, in the y direction. Now, we know that, thinking about it as a geometric sequence, that if I keep multiplying by values, they're going to just get larger and larger and larger. If I keep dividing by values, they're going to get smaller, but you're still going to have some portion of what you started with if you divide. So exponential functions are going to have a horizontal asymptote, because as x's get larger or smaller, we will either bottom out at a lowest point, right, in one direction or another, and that value is going to be directly affected to the vertical shift, right? So if our standard exponential function has like a minimum value that it can obtain, then if we take that minimum value and add to it, then our horizontal asymptote is going to be affected by that vertical shift. So I'll make sure to point these out as we're trying them, right? But let's give a few a try and put them on the graph. So if you're not familiar with just the regular exponential function, let's make sure we go through this. All right? So we're going to start off by graphing 2 to the x. So we'll start by picking a few points just to make sure we can get a basic shape. And then I'm going to select a few of these points to help keep the basic shape going as we start doing these transformations. Right? So in most cases, we pick values of x that are close to 0, because that'll keep the values minimal, right? As long as they're in kind of a standard kind of form, we can kind of see where the values go before they grow out of control, right? So if I put in a value of 0, or put in a value of 1, or put in a value of -1, then we can say, well, anything to the 0 power is 1, right, besides a base of 0, which we can't do. 2 to the first power is 2, and 2 to the negative first power, right, we can move this base to the bottom, right, exponent properties, and it would be 2 to the first on the bottom, which is just a half. So we know that this initial point, right, as we'll call it, because we can write this as 1 times 2 to the x. So even if we don't have like a multiple of a, we can pull that a out as a visual so that we can make this guy get on the graph nice and easy. So a is going to be, at 1, right, when x is 0. When x is 1, y will be 2. And when x is negative 1, y is going to be a half. Right? So we can see that as x gets bigger, this thing is going to be 2 squared, 2 cubed, 2 to the 4th. It's going to grow kind of out of control on this end, right? If I put in negative values, it's going to be 1 over 2 squared, 1 over 2 to the 3rd, 1 over 2 to the 4th. So I'll always have one part of something that is growing out of control. So as x's get smaller, this is where this function is going to approach this asymptote that we have, right? So in terms of a basic exponential function, this thing is going to have an asymptote at 0. It's going to keep getting smaller, but never actually reach 0, because 1 over some continuously large number will still mean you have one part of that. So I'll just kind of draw a dotted line here at 0 to recognize that we have this shape that won't go any lower than that kind of imaginary line there, right? So these 3 points are what I'm going to use as kind of our main points to get these things graphed, right? So I'm going to kind of label them with respect to this standard form here, right? So our first point at our center of our graph, or 0, will be the a value, right? So, when x is 0, we're going to have a y value that's just a, right? If I move 1 unit to the right, then I'm going to have, we could say that this is 1 times 2 to the first, right? So I'll just have my a value, which is 1, times 2 to the first, which is just the b value of 2, right? Because this will be 1 times 1, which is just a. This is going to be 1 times 2, which was 2, so this will be a times b. And if I move 1 unit to the left as like a negative 1, I could say again that this is a times 1 over 2, which was a half, and we can plot that. So what I'll do is I'll say if this is 1 times a, the negative exponents, if you remember your exponent properties, means that we would flip whatever value we have here. So I'm going to write this as, a is itself times 1 over our b value, which will represent the reciprocal of whatever b is. So b could be an integer, it could be a fraction, right? So 1 over b just means it's going to flip. So these guys here is what I'm going to use in this video to move these graphs along. We're going to keep using these points to plot this basic shape. This will be enough to show how much or how fast this thing is growing, or how fast it's getting smaller on each side, depending on which direction this thing is going based on the base. Because if the base is bigger than 1 or less than 1, it could be going down to the right, right? So I'm going to kind of hinge everything that we do on these 3 points here. Right, so we'll practice them. We'll make sure that we got the the asymptote where it belongs, right, as we apply some of these transformations. Okay, so let's try this one. Now that we kind of know what the basic shape is going to be, if you needed a refresher on that or weren't sure, okay, so we're going to try this one with our transformations. I'm going to try to tie them back to stating what the transformations are doing, but we're still going to use those 3 main points to get this to work, right? So what I'm going to do is, we know that the minus 1 here in this exponent is going to be a horizontal shift because it's attached to the x, but the horizontal shifting is going to be backwards from the way we see it. Normally we would think if we want to subtract 1 from the x's, that'll move it to the left 1 unit, but horizontal shifting is going to be backwards. We're going to move this to the right 1 unit. And then this plus 3 is going to be a shift as we would imagine it, right? Plus 3 in terms of the y is going to move it up 3 units. Right? So we can see that it's going to be basically this shape, right, that we just drew, 2 to the x. We can see the 2 to the x here. We're going to move it right 1, up 3. So if we take this shape, we can move it right 1 unit, up 3 units. That means everything about this is going to move in that direction, right? So this horizontal asymptote won't be affected by a horizontal shift, right? But it will be affected by a vertical shift. So if I'm being asked to move it up 3, then this horizontal asymptote would move up 3 units as well. These 3 points that we found will also move right 1, up 3 from these locations, right? So I could see that this guy is going to move right 1, up 3, so 1, 2, 3. Now I'm going to place it on this graph just to show kind of a new method that I'm going to use after we talk about this transformation. This guy would be right 1, up 3. This guy would be right 1, up 3. This horizontal asymptote is going to move up 3. I'll make the dashed lines a little bigger so we can kind of see the new location of this thing with respect to the old location. Right? So we can kind of see how this transformation is going to take this graph and just shift it to a new spot, right? So one method would be to do that. Consider where like the original graph would be and then move all of the points based on the transformations that we do, okay? But I'm going to take this kind of in a different manner. I'm going to say that, well, let's look here. We know that for a basic exponential, right, the origin starts off the location for a times b, a times the reciprocal of b, right? So if I knew this origin point, then I can build these 3 incremental points here very easily by their positions with respect to that origin. So if this function moves to the right 1 and up 3, then it's essentially moving this origin to a new location. So that's how I'm going to treat this. I'm going to say that this -1 is going to move the whole graph right 1 and up 3, which means the origin is going to be moved right 1 and up 3. So I'm just going to kind of mark this as like my new origin. It's not a point on the graph. My origin moved to a new location. I know that my asymptote, my horizontal asymptote, is going to be now at +3. So I will mark that down. We should always be able to see the asymptote based on k. So whatever k is, if you want to just start off by writing that horizontal asymptote, that's not bad. So, like I said, I'm going to treat this like my origin, and now I can just ignore the shifting, and I can think about this in its standard position. This guy has an a value of 1 and a b value of 2, right? I've already compensated for the shift, right? So if I ignore this, then I have an a and a b of 1 and 2, and I'm going to use those points to build this graph off of its new center. So A is just 1. So from our origin, I'm going to go up 1 unit. A times B is just 1 times 2, which is 2. So again, if I go 1 unit to the right, because that's where A times B was, then I'm going to go up 2 from this origin, 1, 2. And if I had gone left 1 unit, it would be A, which is 1, times the reciprocal of B, which just means flip the fraction. If this is 2 over 1, then now it's 1 over 2. So half of 1 is a half. So again, if I go out 1 from our origin, then this will be at a half. And then here I have it. I have my graph. I can see it's going to come down and hug this asymptote. and it's going to come up here and grow out of control. All right, so if I look at these two graphs, right, it's going to be in the same spot. So it just depends on how you want to approach this. Right? I find it to be easier to consider where the new starting location is by use of the shift, and then build that standard position off of its new origin, so to speak. Right? So this is the kind of approach that I'm going to take for these. So let's try another one. Right? So I can see that my standard graph is going to be 2 to the x, right? I do have an a value, which is going to be a vertical stretch since a is bigger than 1. I know that this is going to shift my graph left 2 and down 1, right? So I know I'm going to have an asymptote at -1. So if you want to start off by just putting that asymptote where you know it's going to be, that may not be a bad idea, right? It's the most obvious kind of part of the graph. So if you end up trying something and you have this graph cutting right through this line, then you know that something's not right because the asymptote should be at that vertically shifted value, right? So I'm going to deal with the shift first, and then I'm going to take this standard position a times b to the x and graph it once I know where my new vertex is. Or not my new vertex, my new origin. So this is going to be a shift to the left 2 units, down 1 unit. So from the original origin, if I go left 2 and down 1, this is going to be like my new origin position. It's not a point on the graph, but now I can use the A and B of this basic shape, exponential, from here to build my 3 main points for my shape. So I'm going to start with A. A is 3, right? So from here, I'm just going to go up 3, because this is like my origin. And then if I go to the right 1 unit, I'll use A times B. So 3 times 2 is 6. So remember, from here, not from here, 6. From here, right? 1, 2, 3, 4, 5, 6. And then if I were to have gone 1 point to the right, I can use A times the reciprocal of B, which is 1 over 2, right? 3 over 2 is 1 1/2. So from here, I'm going to go up 1 1/2, right? I know that it's going to come down, but still approach this asymptote. So now I can see that it's coming down not quite as quickly, but it's still going to approach it. And up here, it's going to grow and grow and grow for that up to the right field, right? Because once we get too far away from this origin, it's going to just grow really steep, or in this case, it's going to grow really flat. So closer to that kind of originated turn of the graph gives us kind of the bulk of where that shape comes from. All right, let's try another one. Okay. So again, plus 2 means that my horizontal asymptote is here at 2. Right, makes that pretty obvious. There's no horizontal shift. That's fine, so I'm just going to go nowhere left or right, but simply up 2. So from our origin, the new origin is going to be up here at 2, right? I can say that this negative, because remember, order of operations says we would do exponents before multiplication. So I can think of this guy as -1 times 2 to the x, because the x is only on the base. It's not actually applied to the negative, otherwise there'd be a parenthesis here. Right? So now that I have my new origin, I can use A and B like I normally do. Right? Since A is -1, I'm going to go from here, since it's, A is -1, -1. So from here, I'm going to go down 1 because it's -1. Right? If I go out 1 unit, it would be -1 times 2, which is -2, so I'll just go down instead because they're negative. And if I go 1 unit to the left, it's going to be A times the reciprocal, again, which is 1 over 2, so that'll be -1/2. So from here, -1/2 is about right here. We can see that it's going to come up and approach the asymptote here, it's going to come down and just grow out of control on this right side. Right? So think of the transformations that we talked about, like what A does, what H and K do. We can see that, if we took the original shape, right, right, we know that this function is going to reflect over the x-axis, and it's going to move up 2 units. So if I took this standard position and reflected it over the x-axis, right, since none of it actually touches the x-axis, a reflection would be, since this is 1 unit away, now it'll be 1 unit away down here. This is 2 units away, so it'll be 2 units away down here. Half a unit, right? We can kind of see how that reflection would turn out, right? Because it should be a mirror image here. So instead of thinking about how this reflection gets applied across that asymptote and then moved, right? When we utilize A and B in here, since we're using it as a negative value, it's going to put it below the asymptote just by sake of operations. So we don't have to think about, I need to flip this thing, right? The flipping process comes from these negative outputs. So from our origin, if we had a product that's positive, then it would be above. And if we had a product that's negative, then it would be below. So that'll create that reflection. We don't have to help it along here, right? Again, we can see that if we took this shape, right, thinking about the one we just did, if we took this basic shape, we know that the 3 is going to stretch the graph vertically, right? This is going to shift it left and down. So we can see how this guy isn't quite as steep as this new one was, right? This guy is much steeper from its originated point than this guy was. So we can see where that stretching has come from. This distance here is now 3 times this distance. So 1, 2, 3. You can see how that works out, right? This distance here, 2, is now 3 times that distance. 3 times 2 should be 6. 1, 2, 3, 4, 5, 6. So we can perform these stretches by use of the A and the B values. Right? We don't have to kind of think about the bend. We'll just create the bend through the values that we're plotting. All right, so now we kind of get a sense of how the transformations are working here. Right? Let's jump to some other examples and give a couple a try. Okay, so again, I'm going to look at the -4 to be my horizontal asymptote. 1, 2, 3, 4. So horizontal asymptote here at -4. Nice and easy to spot. I'm just going to go ahead and graph it. Technically, the dotted line isn't a part of the graph. It just helps me establish like where I'm going to go when I start drawing my line. Okay. So this guy is going to go right 3, down 4 to make our new origin. So right 3, down 4 puts it at that asymptote. Right. So now I can think about, again, my basic exponential without the shift, so I can just look at what A and B are. So since A is 3, from our new origin, I'm going to go to 3, right? Then I'm going to do A times B, which is just 3 over 2, which is what? 1.5. And if I had gone to the left, I'll take A. The reciprocal means flip the fraction. So this is 2 over 1. So 3 times 2 is 6. So if I were to go to the left one from our new origin, 1, 2, 3, 4, 5, 6. So we can see that it's going to go down, right, which we anticipated because B is less than 1. So it's going to come down and hug this asymptote because we knew it was going to go down to the right because it's decreasing, right? And up here is where it's growing out of control as it moves to the left. Right? And there we have it. All right, let's try one more. All right, so again, I can see that it's an exponential. I got my variable in the exponent position. I'm going to use 1 as my new asymptote, so I'm just going to go ahead and draw that since it's in shifted form. I know that this +4 is going to move it left, while this one moves it up. So my new origin, 1, 2, 3, 4, up 1, should be on the asymptote. That's why we drew it there, right? Now I can focus on the basic portion of this exponential. I don't need the shifted portion anymore. So I'm going to start with A, which is just -4. So from here, since it's negative, -4, 1, 2, 3, 4. If I move to the right one, I'm going to use A times B. Right? We can multiply fractions straight across. So this is what? -8/3. So what is that? 3 goes into 8 twice. That's 6 with 2 left over. So 2 and 2/3 negative. So 2 and 2/3 is somewhere right there, I guess. And if I move to the left, I'm going to use A times the reciprocal, which is 3/2, right? Multiplying straight across. -12/2, that's -6, right? So, again, if I had moved 1 point, 1, 2, 3, 4, 5, 6. There we go. It's rather steep, right? It's far away from this originated point, so it's going to take a little bit of time to come down here and approach this asymptote, and over here it's just kind of go off into space here. So there we go, right? So as a recap, we can think about what all of these pieces do, right? The 4 is bigger than 1, so it's going to stretch the graph vertically, right? Which is why it was further away from our originated point than we had anticipated, right? It's starting. The negative would be a reflection over the x-axis, right? This guy moved it to the left. This guy moved it up, so left and up, right? This guy would go down to the left. To the right. So if it was going down to the right, we can see that a reflection would bring that shape up here, right? So everything should match up, right? We don't have to think about the transformations. We can kind of use the shift and use these anchor points, so to speak, to create that shape, which should be a byproduct of the transformations that we were looking for. All right, hope that helped.